Excellent. Well, hello everybody on this Friday afternoon. Thank you for coming to the joint CCP-BioSim CCP-EM special seminar. And we are delighted to introduce Joel Greer from CCP-EM. And he is going to be telling us all about his toolkit for benchmarking cryo-electron microscopy reconstruction. So thank you very much, Joel. We're looking forward to it.
Thank you very much, Sarah. So first of all, I'd like to thank Sarah Harris and Sarah Fegan for inviting Martin and I to speak about our work today. So as Sarah mentioned, Martin and I have been equally collaborating on Roodmus, which is a toolkit that we've been working on for analysing heterogeneous reconstruction techniques applied to electron cryomicroscopy data. I'm afraid Martin has been unable to join us today due to some unforeseen personal circumstances, but he's asked me to go ahead and present his section of the slides in his stead. Okay, so what are we interested in? So we're interested in developing tools and performing studies which contribute towards allowing the structural biology community a better understanding of the conformational heterogeneity present in cryo-EM data. So in particular, we've been working to build up an approach which allows in silico simulation of cryo-EM datasets, where by utilising the associated ground truth information from these datasets, we're able to study not only how heterogeneity is dealt with by conventional single particle analysis reconstruction workflows, but also how successfully algorithms which are designed to learn a representation of the heterogeneity present in a cryo-EM dataset are able to actually do so. So these specialist methods, which we term heterogeneous reconstruction algorithms, or HRAs, can be difficult to interpret and validate. So it's desirable to be able to investigate their performance using ground truth information. But before we get further into that, we want to just make sure that everybody's familiar with cryo-EM data and the basics of processing it in order to reconstruct the structure of molecules. So essentially to go from the ensemble of states present in your data set to get a representation of the Coulomb potential of your molecule. Okay, so first you'll need to prepare a sample in the lab of the macromolecule which you want to determine the structure of via cryo-EM. You'll then need to collect thousands of images of individual molecules in your sample to use single particle analysis reconstruction techniques. So to collect those images, you can use a transmission electron microscope. But before you can take any images, you need to prepare your sample to be imaged by the electron microscope. So this is usually done by depositing microliters of a sample onto a holy carbon film, which is usually supported by a copper grid. So we've got some diagrams here and more real examples below. So then once you've deposited your sample onto your holy carbon film, you will blot away any excess to leave a thin liquid layer across the holes in your carbon film. So you then plunge freeze your sample in liquid ethane so that the frozen molecules are still essentially hydrated and are embedded in a thin layer of vitreous or amorphous ice. So these molecules then are frozen in a range of orientations. You can see a diagram back here. So this approach allows your sample to survive the vacuum in the electron microscope whilst preserving the structure of your molecules as much as possible. So after then transferring your plunge frozen sample to your microscope, you keep it at cryogenic temperatures and then image it with an electron beam, and these days commonly also a direct electron detector. In order to avoid damaging the structure of the molecules via radiation damage from the electrons in the microscope, we try and use as small an electron dose as we can. However, that means that your cryo-EM images have quite a low signal to noise ratio, as you can see here. Okay, so once you've collected those images, the first step to getting an estimate of your structure of the molecule is to run a few algorithms, which first of all accounts for the point spread function of your microscope, and correct your images for that. You then need to locate your particles in your images, and then extract essentially a individual particle image for each of them. You then need to estimate the orientation of each of your particle images. So I'll talk maybe a little bit more about algorithms to do that in a couple of slides' time. But once you have an estimate of the orientation of each of your particles, we can take advantage of the Fourier slice theorem. So this states that the Fourier transform of a 2D projection of a 3D object is a central slice through the 3D Fourier transform of that object. So this means we can use, This means that we can use the estimated orientations for each of the particle projections, and compute the Fourier transforms of our particle images, use those along with the orientations that we predict for each of these particle images relative to each other, and piece them together to form of a representation of our Coulomb potential of the macromolecule. So we 3D transform back from this representation into our essentially our normal spatial representation of the Coulomb potential. And then you can repeat this process, iteratively refining the alignments and orientations of your particles until you have a reconstructed 3D density map, i.e. one of these, which is at high enough resolution for you to either be happy with it or perhaps start building an atomic model into it. Okay. So we saw that the reconstruction algorithm is essentially, by necessity, from the signal to noise ratio and the Fourier slice theorem, an ensemble average of the different states or conformational states that might be present in your data set. At room temperatures, we expect our molecules to explore, well, at all temperatures, we expect the states explored by molecules to follow a Boltzmann distribution, and the different states that they can explore allows them to actually perform their biological functions. At room temperature, we expect motion to concurrently exist on many different timescales according to the spatial extent of that motion. So that might range from covalent bond vibrations at femtosecond timescales to maybe backbone fluctuations on the order of nanoseconds, maybe ligand binding on the orders of hundreds of nanoseconds, or maybe collective motions of domains on the orders of microseconds. So proteins in a cryo-EM sample may be expected to be sampling both essentially the main discrete or lower energy conformational states of a protein, as well as the transitive, maybe higher energy states between them at room temperatures. As long as the sample is flash frozen in vitrified ice quickly enough, we expect to be able to see motions of timescales of timescales longer than the freezing process in our cryo-EM sample. Okay, so how can we actually try and access the conformational heterogeneity present within our cryo-EM datasets? So the first way we can do this is to start looking at discrete classification. So one approach you can take is to take advantage of perhaps 2D classification algorithms or 3D classification algorithms, which are a normal step in our computational reconstruction pipeline. So these use maximum likelihood algorithms to group similar looking projections of particles into the same classes, whilst also determining the relative orientations of the particles to each other. So, for example, the average of each 2D class might allow you to see some conformational or compositional heterogeneity in extreme cases, but these are usually used for essentially filtering out any junk in your data set. You're more likely to have success at identifying heterogeneity or discrete heterogeneity using 3D classification approaches. So this is where the user defines a number of discrete classes to group particles into. So the 2D particle images are then randomly assigned to an initial class. The subsets are then refined against some initial consensus model to get n, or the number of discrete classes you've chosen, different 3D density maps. You can then align all of your particle images against these n density maps and determine which class particle is most likely to be a part of. And by repeating this iteratively, you can potentially find discrete conformational heterogeneity in your data set. So, for instance, you might be able to observe the difference between an open and a closed state, or an open state or a closed state of the SARS-CoV-2 COVID spike trimer. But how can we try and identify more continuous heterogeneity in our data set? So in recent years, numerous approaches have been used to try and approach this problem. We collectively refer to them, as I mentioned earlier, as heterogeneous reconstruction algorithms. So here I'll focus on a particular subset of these approaches, which aim to embed all of the 2D particle projection images in a low-dimensional latent space by using an encoder network. So this is a convolutional neural network. They also comprise a decoder network here, which learns how to translate the latent space representation back into a volume space representation. So essentially a cryo-EM density map at a particular coordinate of this latent space. So to give you an example, here's a heterogeneous reconstruction algorithm I trained earlier. So here I show the latent space of a two-dimensional UMAP embedding. So here I show both a hex bin representation to show you exactly the proportion of particles which are present at each position in this embedding. And I also show you a scatter plot. So here, each of these tiny blue dots corresponds to one particle image, and exactly where the embedding of the heterogeneity is in this latent space representation of heterogeneity. So here on this latent space, I've then I've performed a k-means clustering with 20 in order to find 20 representative particles, which essentially represent the range of heterogeneity present in the data set. I've then, in this semicircular manifold, I've then gone and used the decoder network to decode each of these coordinates into a volume representation. So here are a few of those volume representations starting at 6 and going through 8 around this semicircular manifold. Show you exactly how the representation of heterogeneity is embedded in this latent space embedding. Okay, so there are a number of different ways to use VAE-based methods to represent the heterogeneity present in cryo-EM datasets. Most of these use similar encoder networks, but they can use slightly dissimilar decoder networks or approaches to decoder networks. So one approach is CryoDragon, which is the algorithm that I was using in the previous slide. So in this case, the decoder directly outputs a 3D volume density representation from a given latent space coordinate. So this approach is able to handle both conformational and compositional heterogeneity in datasets, but it doesn't explicitly model any protein motion or preservation of local geometries. 3D Flex outputs a deformation field, which specifies the way that a consensus reconstruction should be deformed to reach a specific conformational state, according to a given sampled coordinate in the latent space. So this is suited for encoding conformational heterogeneity or continuous conformational heterogeneity, whilst also explicitly modeling protein motion and preserving local geometry through the conformational landscape. So one other approach is Dynamite. So in this case, the conformations in the cryo-EM dataset are represented by essentially learning the 3D deformation field of a pseudo-atomic model composed of Gaussians. So each of these Gaussians represents a part of the Coulomb potential. You can then use the learned deformations to either obtain an improved reconstruction of a consensus structure, or you can then, well, one other thing you can actually do, or this method, sorry, is designed to deal, once again, like 3D Flex, with more continuous conformational heterogeneity rather than compositional heterogeneity. One notable feature about it, though, is that it trains two separate variational autoencoders on essentially half sets, so independent half sets of your particle images. And this allows it to give you an estimate of the error in the deformation field projection that it makes. Okay, so we've got these heterogeneous reconstruction algorithms that we'd like to use, but how do we know that these methods are actually functioning as we expect them to? Are the latent space representations of heterogeneity organized in some kind of sensible or interpretable way? We know that the latent space representations are inherently nonlinear, which can make them challenging to interpret. Are the estimated volumes or deformation fields from the decoder networks representative of the actual atomic models of a macromolecule in a given image? Now, remember, there's no ground truth for the conformations of particles in experimental data sets. So it's impossible to know this just by looking at experimental data without any ground truth information. So what we'd like to do is to start investigating what the accuracy of the predicted conformational states are. Are intermediate states in molecular motion ordered in a sensible or chronological order? That's in the latent space. Also, what kind of quality does the input data need to have for continuous conformational changes to actually be observable using heterogeneous reconstruction algorithms? So in order to actually attempt to address and answer all these questions, we've designed the Roodmus Toolkit. So this is a framework to allow for the simulation of high-quality synthetic data and tracking of concomitant ground truth information. So we source our conformational heterogeneity from MD simulations. We sample the different conformational states, i.e. atomic models, and then we use a software package called Parakeet, which was developed at the Rosalind Franklin Institute by James Parkhurst, to simulate whole synthetic cryo-EM micrographs. So these contain the particles sampled from the MD simulations in those conformations. So many parameters in these simulations are configurable in addition to the sample, such as those for the beam, lens, and detector in the microscope. And these particles are randomly oriented in position throughout the sample, much like you would expect in a nice experimental data set. So these micrographs can then be processed using standard reconstruction approaches, like the one I introduced earlier, as if they were experimental micrographs. You can also use them as the input to heterogeneous reconstruction algorithms. And by using the ground truth information, you can track the performance of your reconstruction algorithms or try and understand how they're organizing your data using your ground truth information. Okay, so Roodmus allows us to generate datasets from MD trajectories. So what MD trajectories are we going to use in our investigations? So to perform the studies that we show here, we've used MD trajectories performed by D. Shaw Research, published in 2020 from their MD simulations related to SARS-CoV-2 dataset. So these are long simulations, which we hope to allow sufficient conformational heterogeneity to be present in for heterogeneous reconstruction algorithms to actually be able to find representations of continuous heterogeneity. So we chose the SARS-CoV-2 spike glycoproteins, in particular the partially open conformation, because the receptor binding domain around here has been found to be reconstructed from experimental datasets with lower local resolution than the rest of the protein in this conformation. in this open state, and provides us with a reasonable reference point for a region of increased conformational heterogeneity. We also choose the closed spike trimer glycoprotein. So this then allows us to investigate how conformational heterogeneity can be encoded at the domain scale, particularly with relation to the partially open COVID spike trimer simulation. So essentially that gives us two discrete states that we can investigate the encoding of heterogeneity for. We've also used a long NSP13 bound SARS-CoV-2 replication transcription complex simulation. So this one is 500 microseconds in total, with each frame being 4.8 nanoseconds separated. So we chose this to allow us to investigate heterogeneity present over as long a timescale as possible. So we use these MD simulations to create synthetic micrograph datasets using Roodmus. Okay, so first of all, we'd like to investigate how conformational heterogeneity, or the presence of it in the dataset, impacts cryo-EM reconstructions. So to do this, we generated two datasets from the DE-Shore MD simulation of the glycosylated SARS-CoV-2 spike protein in its partially open conformation. So for this first data set, we extracted just a single conformation from the MD simulation, so just one, and used Roodmus to simulate 34 micrographs containing 10,200 occurrences of this particle. So each of those has exactly the same conformation. We then created a second data set, for which we extracted all of the conformations from this MD simulation, so 8,334 in total, and simulated a data set of 270,000 particles. So here we show an ensemble of a few of these different conformations. So this data set was generated to be so large in order to also be useful for later analyses, and to make sure that we include multiple viewing angles of each conformation, which is useful for our later studies of heterogeneous reconstruction algorithms. Okay. So in order to compare the single particle analysis reconstructions from the two datasets, we make sure to apply the same process when reconstructing our density maps from our synthetic micrographs. So we use Reliant for this, a standard single particle analysis tool. So here I show an example of the pipeline that we've used for the single conformation dataset, but we use essentially the same pipeline for the multiple conformation dataset. At the end here, the thing to note is that at the end, we randomly subselect 8,000 particles to do a subsequent final refinement on and generate our final consensus density map. Okay. So we've taken picked particles here from the single conformation dataset, reconstructed a consensus density map. So here, these results are purely for the single conformation dataset and the reconstruction of it. So to understand the quality of the reconstruction, we want to determine the resolution of the reconstruction and also get an estimate of how much the signal is attenuated at higher resolutions by a combination of factors from imaging and from the computational reconstruction, often combined together and called a B factor. So the factors from imaging, in our case, include just the detective quantum efficiency, but don't include other factors in this data set, such as specimen movement, charging, radiation damage, or inelastic scattering, or even, very deliberately in this case, any particle conformational heterogeneity. However, the factors from computational reconstruction are still present, including estimation of the particle orientations and translations, and also estimations of the microscope parameters in our reconstruction pipeline. So to estimate the resolution, conventional practice is to compute the Fourier shell correlation. So to do this, you split your data set in half to get two half maps. You then apply a mask around these to remove any noise from regions outside your protein structure, before then Fourier transforming these volumes and calculating the Fourier shell correlation. So this is a correlation coefficient between successive spherical shells in Fourier space. And by convention, the value of the spatial frequency, where the Fourier shell correlation crosses 0.143, is taken to be the global resolution of the map reconstructed from your whole data set. So in this case, we find a global resolution of 2.29 angstroms for this single conformation data set. We also compute the local resolution here using the ResMap program. So this is essentially a per voxel estimate of the wavelength that a local feature is present at. And this is determined statistically by performing a likelihood ratio hypothesis test between a local sinusoidal model with that wavelength against the background noise. So we observe from this data set a largely uniform local resolution, unsurprisingly very close to the global resolution, well, unsurprisingly because of our lack of conformational heterogeneity. So we see a slight decrease in the local resolution at the borders of our reconstruction. That might be due to small misalignments of particle images during the reconstruction process. So finally, in order to get a sense of exactly how much our signal is actually attenuated, we compute the B factor via a reslog plot. So this is where we take subsets of our total particle sets and compute the resolution of each of these subsets using the FSC, as I explained above. And then we compute the gradient of this best fit line, which allows us to get an estimate of the B factor. So in this case, we find a very low B factor of 17.8 angstroms squared, which means there's essentially not very much potentially motion in this data set. And this B factor can essentially be attributed purely to errors in steps of processing. So maybe errors in the alignment or orientation of our particle images. So for reference, for B factors, you might be unable to manually fit an atomic model at higher values of a B factor, maybe around 150 or 200 angstroms squared. Okay, so we've seen what we get from reconstructing our single conformation dataset using a single particle analysis pipeline. So I show here the same plots as on the previous slide on the top level here in this subfigure A. And now I also show the same plots for our dataset, which includes conformational heterogeneity. Okay, so the only difference between these two data sets is essentially the presence of conformational heterogeneity in the second data set. We're using the same number of particles in both of these reconstructions. So on this occasion, we find that the global resolution decreases quite significantly to 3.17 angstroms. When we compute the local resolution of each voxel, we see that this is also much lower than for the single conformation data set. And that is purely a result of the increase in conformational heterogeneity and potentially problems that causes for the reconstruction pipeline in the estimation, in the alignment and estimation of the orientation of each of the particle images. So performing a reslog analysis on this data set to find the B factor, we find that the B factor is 41.1 angstroms squared. And that is increased, we presume, essentially due to just the increased heterogeneity, the conformational heterogeneity present in this data set. So this is still maybe much lower than we would expect from an experimental data set. And this may be due to a lack of a number of physical factors being present during simulation of the synthetic data. And that might mean that the resulting alignments during reconstruction aren't perhaps as challenging as they might be for experimental data sets. Okay. So next, we'd like to look at exactly exactly how a discrete classification actually performs on datasets which are composed with or composed of discrete heterogeneity. So here we're interested in can our 3D classification actually separate out discrete heterogeneity in our synthetic cryo-EM micrographs. So in order to do this, we created a hybrid dataset utilizing both the partially open and closed COVID spike trimer MD simulations from DE Shaw. In total, we generated 120,000 particles, so 60,000 from the closed state simulation and 60,000 from the open state simulation, and reconstructed those to get an initial consensus reconstruction. So we then performed 3D classification with a varying number of classes to identify how these discrete states were classified. Okay, so first of all, we used two classes. So you can see here that in class 1, this was composed essentially pretty much purely of particles from the open state MD simulation, whereas class 2 ended up being composed of particles from a mix of both the closed state and the open state, but many fewer particles from the open state MD simulation. So we then used our ground truth information to compute the precision of the particle picking in each of these classes. So we find that for the second class, we actually have the presence of some false positive particles, which are essentially junk or noise. And we also find through the combination of both these junk particles and also the split of our particle images into these two different classes, we find that the majority of our particles are essentially put into class 2. Right, but what we also want to figure out is which class, now remember each has a reconstructed density map, which of these reconstructed density maps is most similar to the actual atomic models from the open state and the closed state MD simulations. So to do this, we computed the real space map to model correlation between atomic models sampled from the open and sampled from the closed state MD simulations, so 50 from each. So here we show the real space, map to model real space correlation normalized for each class. And you can see that class 1, unsurprisingly, correlates much more strongly with atomic models from the open state MD simulation, and class 2 correlates more strongly with atomic models from the closed state MD simulation. So what happens if we then increase the number of classes to 3? So here we see, in this case, class 1 is essentially purely composed of particles from the open state MD simulation. Class 1 is, and then class 3 is composed of particles essentially purely from the closed state MD simulation, but class 2 has a mixed composition. So we find that false positive particles are also sorted into this mixed class in this also on this occasion, and that it has the most particles put into it overall. However, the actual global resolution of class 2 ended up being lower, about 2.8 angstroms, than that for either class 1 or class 3. So these were about 2.5 and 2.6 angstroms. So once again, by computing the map to model real space correlation between atomic models sampled throughout the open and closed states and each of the density maps from these classes, we find that, as expected, class 1 has a much higher correlation with the open state, class 3 with the closed state, but class 2 is much more mixed. Okay, so here we show the actual refined density maps for each of those 3 classes. So here we've thresholded them all at the same contour level, So that's what these colored isosurfaces are. But we've also determined isosurfaces using a statistical technique, i.e. false discovery rate controlled maps. So this is where we set the probability of essentially false discovery of the density to 10%. And you can see these false discovery rate controlled maps plotted here as these black outlines around the colored isosurfaces. So using these FDR controlled maps, we see significant variations in the presence of density around the region where we expect the receptor binding domain of the COVID spike protein to be, which is pointed to by this arrow. So for class 1, we see evidence for density in this region. That's unsurprisingly because this class is mainly comprised of particles from our open state MD simulation. In class 3, we don't really see any evidence for this, once again, because it's composed of particles from the closed state. And then for class 2, which is composed of a mix of these open and closed state particles, we see some evidence. Okay, so we've investigated discrete heterogeneity. What can we learn about how heterogeneous reconstruction algorithms actually represent or are able to represent continuous heterogeneity? So what we've done here is we've gone back to using our synthetic data set that we've generated with Roodmus from the partially open COVID spike trimer MD simulation. So this is where we had 270,000 particles we simulated. We can actually pick 236,000 particles from these synthetic micrographs. And what we've done is trained cryo-dragon, one of the heterogeneous reconstruction algorithms, with an 8-dimensional latent space on these particle images. So here I show a 2-dimensional embedding of the latent space for this trained cryo-dragon model. So here you can see that essentially it's very difficult to a priori interpret any structure in this latent space. If we start using our ground truth information that we've got with our synthetic data set and plot the false positive particles, i.e. anything which is essentially just actually noise or junk, then we can see that there's maybe some grouping towards the center, but it's still quite a diverse spread. So what happens if we use more of our ground truth information to help us interpret this latent space embedding of cryo-dragon's latent space? So what we've done here is, because we can track each of our individual particles and the conformation of that particle back to a time point from the MD simulation, what we've done here is we've colored each of our particles in the latent space embedding by the time at which that conformation occurred in our MD simulation. So you can see there that you can potentially start to track the MD simulation's path through the latent space embedding from start to finish. Now, in order to actually do that, what we did is we grouped the MD simulation into 50 batches of conformations, i.e. the first 2% of the frames of the MD simulation, and then the next 2%. And then for each of these batches of conformations, we computed the average position in the latent space embedding of the particles which were present in that data set. Sorry, which were present in that batch. So what we've done there, so we've plotted these average positions in the latent space with these black dots here, tracing through from the start of the latent space, i.e. the first 2%, all the way through to the end. And you can see that that from our knowledge of the ground truth information, we can actually see that this latent space embedding is potentially reasonably sensible, and actually allows us to track the MD simulation contiguously in time through the latent space embedding. Okay, now remember that this latent space embedding, you can take any point in this latent space and decode a volume representation of the conformational heterogeneity at that particular point in the latent space. So what we've done here is we've taken each of these average positions from each batch of conformations from the start to the end of our MD simulation, and we've decoded a volume representation for each of these. What we've then done is we've extracted atomic models throughout our MD simulation, and we've computed the map to model real space correlation between the extracted atomic models and between the density maps that we've extracted from these locations or decoded from these locations in the latent space. So we compute the real space map to model real space correlation between these, and we see that we actually get a much higher correlation between atomic models and sampled volumes, which are essentially close in time in the MD simulation to each other. So here, a high correlation value is expected to be about 0.7, and a low correlation generally expected to be about 0.5. Okay, so we've also used this approach on our SARS-CoV-2 replication transcription complex dataset. So we generated a dataset of 50,000 particles, of which we can pick 41,000 of those. You can see that in this particular dataset, if we do a standard single particle analysis reconstruction and show the local resolution, we have a much more conformationally homogeneous region in this core and much more heterogeneity out towards these extremities. Once again, the latent space is quite difficult. So once again, we train CryoDragon using these picked particle images on this data set. If we then look at the two-dimensional latent space embedding, this is just a priori still quite difficult to interpret. But if we use our ground truth information, we can reasonably well track this through from start to end in the same manner as we did previously for the COVID spike trimer dataset. So we see that the latent space is explored quite a lot up to about halfway through the MD simulation. So maybe that's essentially up to sampled volume 20 here. And once again, we decode volume representations at these positions in our latent space, and compute the map to model real space correlation against atomic models sampled throughout our MD simulation. So up until this essentially 20th sampled volume, we do see indeed that we get a much stronger correlation between these maps and models according to essentially how close they are in time in the MD simulation. But once we get to this more densely populated region of the latent space, we start to see higher correlations between the decoded volumes and the atomic models. So this potentially suggests that we see less conformational heterogeneity in this region of the MD simulation, or potentially the heterogeneous reconstruction algorithm struggles to separate out the actual conformational heterogeneity present in the data set. And that's something that we need to look further into in the future. Okay, so we've seen that Roodmus, or our Roodmus toolkit, allows us to investigate the impact of heterogeneity on reconstructions by utilizing our ground truth information from MD simulations. we've seen that discrete classifications don't always result in well-separated classes. And we've seen that heterogeneous reconstruction algorithms do potentially allow you to represent a continuum of structural states in your latent space embeddings. And that the decoded volumes can represent the actual states present in the data set quite well. So now we'd like to give you a taste of what we're looking at doing in the future. So there's a number of things. So one thing we're looking at doing is that whilst Parakeet provides a good simulation of synthetic micrographs, there's scope for improving these simulations by introducing some more physical effects, which would occur during data collection in an actual physical experiment. We're also interested in looking at decreasing the quality of our simulated data sets to determine at what point, perhaps with low signal to noise ratio, heterogeneous reconstruction algorithms begin to be unable to recover heterogeneity. And we could also start looking at the impact of experimental pathologies like preferred orientation. So we've run a couple of steered MD simulations to investigate how heterogeneous reconstruction algorithms actually encode simple continuous motion. So what we've done here is we've taken the human C3b complement protein, and we've run an MD simulation where we have two intermediate states that we steer it towards, and it stays in for a short amount of time, and then we steer it towards a final state, which it also stays in for a short amount of time. So see here, steer it towards the first intermediate state, the second intermediate state, and then into a final state. So from this MD simulation, you might expect that potentially a heterogeneous reconstruction algorithm might be able to find 3 more kind of discrete clusters of conformational arrangements in the latent space embedding. So here I just show as well an ensemble of some of these states throughout the simulation. But if we look at the 2D embedding of the latent space, so here we've trained 3D Flex rather than CryoDragon, and we've trained it using a 2-dimensional latent space. So if we look at the actual latent space embedding here, then we see that if we use our ground truth information to understand how the conformational heterogeneity is actually embedded, we see that there are potentially 3 maybe discrete clusters. So the start of the MD simulation, maybe up until the first interim state, then maybe the second part of the MD simulation up until the second interim state, and then the final state. But we see that these are not arranged in a manner where they can be traversed in a continuously in the latent space on this occasion. So essentially, be aware that traversing latent space representations of heterogeneity is non-trivial, and potentially we would like to look at that optimizing different hyperparameters for each of these different methods and looking at the effect of that. Okay, so protein dynamics gives us insight into how proteins function. To better understand that, we want to know what the equilibrium populations of discrete conformationally favorable states are, as well as what the transitive pathways are between them. So in our work so far, we've concentrated on understanding whether the continuous heterogeneity present in our MD datasets can be visually interpreted in embeddings of the learned latent representation, and whether the decoded volume representations are more similar to atomic models from the MD simulation frames, which we would expect them to be most similar to, i.e. those which are close in time. However, latent space representations are inherently nonlinear and may depend on hyperparameters used during training. So therefore, we'd like to both develop and evaluate methods which seek to find continuous transitive pathways between states, as well as discrete conformational states themselves. So one such example of that is cryo-Dragon's conformational landscape analysis, but I won't go through that now, just in the interest of time. One other thing that we'd like to investigate further is actually developing metrics for heterogeneous reconstruction algorithm representations of heterogeneity. So, for example, one approach we're currently looking into is inspired by this paper from Tiberti et al. So here they essentially do two MD simulations of a protein to get two different ensembles. They then compute essentially a distance calculation between all of these conformational states, and through either some clustering or some dimension reduction and then clustering, they then compute a measure of similarity between each of the different states via this metric called the Jensen-Shannon divergence. So we'd like to do this both for the MD simulations that we use to create our synthetic datasets, but also for the clusters that we derive using heterogeneous reconstruction algorithms and essentially looking at the clustering of the latent space, or potentially clustering of the volume space representations from these heterogeneous reconstruction algorithms. So one other thing we're interested in starting to investigate is what scales and resolutions of heterogeneity heterogeneous reconstruction algorithms are actually capable of encoding. So we'd like to start looking at small conformational changes, potentially those caused by maybe the induced fit of a ligand, or potentially maybe whether we're able to use these algorithms to detect the occupancy of a ligand in a data set. We're also interested in longer timescale motion, whether that's from long atomistic MD simulations, or potentially even extending Roodmus to be able to deal with coarse graining or coarse-grained models. So there have been studies which have looked at these things previously in experimental data sets, but once again, in the interest of time, I won't go through that now. But one other thing we're interested in looking at is the current limits of heterogeneous reconstruction algorithms with current instrumentation, and potentially what developments in instrumentation in the future would be required to overcome any of these limitations. So much of the future work which we'd like to do utilizing Roodmus will depend on the generosity of the MD community. So we'd like to continue to investigate how different scales and types of heterogeneity are represented by heterogeneous reconstruction algorithms using our approach with Roodmus and utilizing our ground truth information in synthetic data sets. But to do this most effectively, we'd like to ask for your guidance on MD trajectories to look into, but also if you're willing to, please do feel free to contribute MD simulations. One of the things that we'd like to use Roodmus for is potentially running community challenges for HRA heterogeneous reconstruction algorithm developers in the future to allow periodic evaluation against ground truth information. But we're also interested in any opinions or suggestions you might have on benchmarking metrics, or potentially also if you have MD simulations which also have accompanying experimental data sets. So that might be with perhaps a view to investigating whether these experimental data sets can be used to aid MD simulation or sampling. So at the moment, Roodmus can handle protein and nucleic acid as long as essentially the protein membrane isn't present. So ideally, we'd like to be able to just approach these data sets as if they were normal single particle analysis data sets. And currently, we recommend Roodmus is run on datasets, particles which are smaller than about 750 kilodaltons. So that's just a limit on essentially the speed of the simulation, but we're working on parallelizing the simulation to try and help with that. Okay, so in particular, I'd like to thank and acknowledge Dr. Tom Burnley and Dr. Ian Jacobi, who have given invaluable guidance and advice throughout this work. I'd also like to thank everybody else here that I put on this slide. Parts of this work would not have been possible without them. So I've also put QR codes here for Roodmus's GitHub page and for our current bioarchive. But if you would like to get in contact, please do email me at this email address here. So yeah, thank you very much for listening. I'd be happy to answer any questions.